Episode 31, titled VXLAN, What Overlays Enable and Why Architects Use Them, we frame Virtual Extensible Local Area Network as a way to extend segmentation across large routed networks, because overlays exist to preserve logical grouping even when physical networks scale beyond what traditional Layer 2 can handle cleanly. The exam uses this topic to test whether you understand why architects reach for overlays in modern data centers and hybrid environments, not whether you can memorize header formats. Overlays solve a practical tension. Workloads still benefit from consistent segmentation and familiar Layer 2-like grouping, but the underlying network must be scalable, resilient, and routable at Layer 3. Virtual Extensible Local Area Network addresses that by carrying logical segments over an Internet Protocol transport, allowing segmentation to span racks, pods, or even sites without forcing the physical network to behave like one giant broadcast domain. When you grasp the underlay and overlay separation, you can answer scenario questions about scale, tenant isolation, and multi-rack connectivity with a steady mental model. The goal is to make Virtual Extensible Local Area Network feel like a clear architectural tool that depends on a healthy underlay and delivers flexible overlay segmentation. Before we continue, a quick note. This audio course is a companion to the CloudNet X books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. The overlay concept is the key idea, and it can be summarized as encapsulating Layer 2 inside Layer 3 transport, so the network can scale while segments remain consistent. Encapsulation means you take an original frame that belongs to a logical segment and wrap it in an outer packet that can be routed across the underlay network like any other Internet Protocol traffic. The underlay sees the outer packet and forwards it based on normal routing, while the overlay endpoints remove the encapsulation and deliver the original frame to the correct logical segment. This is powerful because it decouples logical segmentation from physical topology, allowing you to move workloads and preserve segment identity without reconfiguring every intermediate switch to carry a particular virtual local area network. It also reduces dependency on Layer 2 spanning mechanisms that can become fragile at scale, because the underlay can remain a clean Layer 3 fabric with predictable routing. In exam scenarios, when you see overlay, encapsulation, or extend segments across a routed fabric, Virtual Extensible Local Area Network is often the technology implied. The main mental model is that the overlay defines who belongs together, while the underlay defines how packets travel between overlay endpoints. A virtual network identifier, commonly shortened to VNI, is the label that maps segments across many physical locations, and it functions like the overlay's segment identity. Instead of being limited by traditional Virtual Local Area Network identifier space, Virtual Network Identifier provides a much larger identifier space that supports many segments and many tenants. The practical impact is that a workload can be part of a segment identified by a specific virtual network identifier regardless of which rack or node it resides on, as long as the overlay endpoints know how to reach each other. This mapping allows consistent policy, consistent addressing schemes, and consistent isolation across a large fabric, even when physical placement changes. In shared environments, Virtual Network Identifier is a key ingredient for multi-tenant isolation because it prevents traffic from one tenant segment from mixing with another tenant segment even while sharing the same underlay. In exam logic, when the prompt mentions many segments, tenant isolation, or large-scale segmentation, Virtual network identifier is the concept that explains how overlays avoid identifier exhaustion. The important point is that virtual network identifier is not just a number. It is the binding that makes a logical segment portable across the physical fabric. Traditional virtual local area networks struggle across scale and distance because Layer 2 domains become hard to control when they stretch too far, and operational complexity grows quickly as you try to extend them. Virtual local area networks are effective within a local switching environment, but extending them across many racks or sites often requires complex trunking, careful spanning control, and meticulous allowed lists, which increases the risk of leaks and makes troubleshooting slower. Broadcast and unknown unicast behavior can also become noisy when a Layer 2 domain spans too broadly, and that noise can consume bandwidth and obscure anomalies. There is also practical identifier scale pressure because environments can outgrow simple role-based virtual local area network models when many tenants, environments, and microsegments are required. As data centers adopt fabric designs and as workloads become more dynamic, the desire to keep the underlay simple and routable becomes stronger. Virtual extensible local area network is attractive in this context because it lets the underlay be a scalable Layer 3 network while still providing the segmentation abstraction that operators and applications often rely on. In exam scenarios, when the prompt describes scaling pain with traditional virtual local area network trunking, virtual extensible local area network is often the modernization path being tested. A practical selection rule is to use virtual extensible local area network when many segments must span multiple racks or sites, because it provides portable segmentation without forcing the physical network to carry every segment everywhere. In a multi-rack environment with many application tiers, tenants, or environments, virtual extensible local area network can reduce the need for widespread trunking and reduce the risk that sensitive segments traverse links unnecessarily. It also supports mobility because workloads can move without needing the physical network to be reconfigured for that segment, as long as the overlay endpoints are present where the workload lands. For multi-site, the same logic applies when the goal is to extend a logical segment across distance while keeping the underlay routed and scalable. The exam often hints at this with phrases like spanning segments across racks, multi-tenant isolation, or overlay network required, and those cues point toward virtual extensible local area network as a fit. The key is that virtual extensible local area network is not the default for every network. It is a tool used when segmentation scale and mobility requirements exceed what traditional Layer 2 extension can manage safely. When you see those scale and mobility signals, overlays become the natural architectural move. Underlay requirements are non-negotiable because virtual extensible local area network depends on reliable Internet Protocol connectivity and stable routing, and overlays do not fix underlay problems. The underlay must provide consistent reachability between overlay endpoints, and it must handle the encapsulated traffic reliably, including appropriate routing, path redundancy, and performance characteristics. If the underlay has intermittent loss, unstable convergence, or asymmetric path issues, the overlay inherits those problems and often makes them harder to diagnose because failures can appear as overlay anomalies. The underlay also needs appropriate capacity because encapsulation adds overhead and because overlay designs often increase east-west traffic across the fabric. In exam reasoning, when a scenario describes overlay issues, a strong candidate answer often checks underlay stability first because an overlay cannot be healthier than its transport. This is why architects treat underlay and overlay as separate layers with separate monitoring, because each has its own failure modes. The main lesson is that overlays are abstractions built on transport, and the transport must be healthy for the abstraction to behave predictably. Control plane behavior determines how overlay endpoints learn where to send traffic, and you will often see this expressed as learn and flood versus more distributed route-style information sharing, such as Ethernet VPN-style distribution. Learn and flood means that when an endpoint does not know where a destination is, it may flood within the overlay segment until it learns the correct mapping, which can work but can create noise at scale. A more distributed approach advertises reachability information so endpoints can make informed forwarding decisions without relying on flooding behavior, which generally improves scalability and reduces unnecessary broadcast-like traffic. The exam does not require you to master every control plane detail, but it often expects you to understand that control plane choices affect scale, stability, and troubleshooting. If the environment is large and multi-tenant, control plane distribution that reduces flooding tends to align with predictable performance and operational simplicity. If the environment is small, simpler learning models may be adequate, but the architecture must still consider the traffic patterns and noise tolerance. In scenario terms, when the prompt emphasizes scale and many segments, answers that reduce flooding and improve distribution are often favored. The key is to connect control plane choice to observable behavior, such as how quickly endpoints learn mappings and how much noise is introduced. A common scenario for virtual extensible local area network is tenant isolation in a shared data center fabric, because it allows multiple logical segments to coexist over the same physical infrastructure without mixing traffic. In a shared environment, tenants may require separate address spaces, separate segmentation boundaries, and strong isolation guarantees. Yet the operator wants to avoid building separate physical networks for each tenant. Virtual Network Identifier provides the segmentation label, and the overlay ensures that traffic for one tenant stays within the tenant's logical segment even while traversing shared underlay links and switches. This supports operational efficiency because the fabric can be standardized while tenant networks remain logically distinct and policy can be applied per segment. It also supports growth because new tenant segments can be created without redesigning the underlay, as long as the overlay endpoints and control plane support the expansion. In exam scenarios, when you see multi-tenant, shared fabric, or isolation across racks, virtual extensible local area network is often the intended technology because it aligns with scalable, logical segmentation. The best answers usually acknowledge that isolation depends on both correct overlay configuration and healthy underlay routing. A major pitfall is underlay instability, making overlay troubleshooting confusing, because symptoms can appear at the overlay level even when the root cause is packet loss, routing flaps, or path asymmetry in the transport network. When packets are encapsulated, intermediate devices see only the outer headers, and if the underlay drops or misroutes those packets, the overlay may appear to have endpoint reachability issues that feel like mapping failures. Operators may chase overlay configuration, control plane tables, or virtual network identifiers, while the real problem is a link that is flapping or a routing policy that is unstable between overlay endpoints. This is why monitoring must explicitly distinguish underlay health from overlay health, because mixing them creates blind spots. In exam reasoning, if a scenario describes overlay flaps or intermittent tenant connectivity, a strong answer often involves verifying underlay stability and routing convergence before changing overlay mappings. The principle is simple. Encapsulation hides details from intermediate devices, so a transport failure can be harder to see unless you monitor it deliberately. Overlays simplify segmentation but can complicate fault isolation if the underlay is not treated as first class. Another pitfall is maximum transmission unit mismatch, causing fragmentation and performance issues, because encapsulation adds overhead and can push packets over the path's effective size limit. When the outer headers are added, the encapsulated packet becomes larger than the original, and if the underlay path cannot carry that size without fragmentation, packets may be fragmented or dropped depending on network behavior. Fragmentation increases overhead and can reduce throughput, while drops can cause retransmissions at higher layers that feel like application slowness. Maximum transmission unit mismatches are especially painful because they can create selective failures, where small requests work but large transfers fail, which is confusing without an awareness of encapsulation overhead. In exam scenarios, clues like small packets succeed but large transfers fail, or performance degraded after enabling overlay, often point to maximum transmission unit configuration and path consistency issues. The best answer typically involves ensuring consistent maximum transmission unit settings across the underlay and overlay endpoints so encapsulated traffic fits cleanly. The key is that overlay designs require you to budget for header overhead, and failure to do so becomes a stealth performance killer. There are quick wins that improve reliability, such as monitoring both underlay and overlay health consistently, because layered systems require layered visibility. Underlay monitoring should include reachability between overlay endpoints, routing stability, loss, latency, and maximum transmission unit consistency across key paths. Overlay monitoring should include segment membership, endpoint mapping health, control plane stability, and tenant reachability tests that reflect real service flows. Consistent monitoring matters because it allows you to correlate symptoms, such as whether an overlay outage aligns with an underlay routing flap, which speeds root cause identification. It also helps prevent blaming the wrong layer, which is a common operational mistake when overlays are introduced. In exam reasoning, answers that include both underlay and overlay validation tend to align with best practice because they acknowledge the two-layer dependency model. The practical lesson is to treat the overlay as a service on top of a transport and to monitor both layers as separate but related domains. When you do that, troubleshooting becomes methodical rather than speculative. A useful memory anchor is underlay carries packets, overlay defines tenant segments, because it keeps responsibilities separate and makes troubleshooting clearer. Underlay carries packets means the physical or routed network is responsible for reliable transport between overlay endpoints, including routing convergence and capacity. Overlay defines tenant segments means the logical network identities, segmentation boundaries, and endpoint mappings are created at the overlay layer using virtual network identifiers and control plane mechanisms. This anchor also helps you interpret exam prompts that mix terms, because you can ask whether the problem described is a transport reachability problem or a segment mapping problem. When you can keep these responsibilities distinct, you are less likely to assume overlays solve underlay instability, and you are more likely to design monitoring and policy correctly. It also clarifies why maximum transmission unit and routing stability are underlay concerns, while segment isolation and mapping are overlay concerns. The anchor is a simple way to keep the architecture clean in your mind. To end the core, narrate a packet path through the encapsulation steps, because doing so forces the overlay concept to become tangible. A workload sends a frame intended for another workload in the same logical segment, and the local overlay endpoint recognizes the segment identifier and determines the remote endpoint that hosts the destination. The endpoint encapsulates the original frame inside an outer Internet Protocol packet, setting the outer source and destination to the underlay addresses of the local and remote overlay endpoints. The underlay routers forward this outer packet like normal routed traffic, unaware of the inner layer 2 content and focused only on delivering the outer packet to the correct endpoint. When the remote endpoint receives the packet, it removes the encapsulation, recovers the original frame, and delivers it into the correct logical segment associated with the virtual network identifier. The destination workload receives the frame as if it were on a local segment, even though it traveled across a routed fabric. When you can narrate this sequence, you can reason about where a failure could occur, whether in underlay transport or in overlay mapping and delivery. In the conclusion of episode 31, titled VXLAN, What Overlays Enable and Why Architects Use Them, the main fit criteria are segmentation scale, mobility across racks or sites, and the desire to keep the underlay as a clean, stable Layer 3 fabric. Virtual Extensible Local Area Network encapsulates Layer 2 inside Layer 3 transport using a virtual network identifier to map logical segments across physical locations and support large numbers of isolated segments. It is often chosen because traditional virtual local area networks struggle to scale across distance and complexity, while overlays preserve logical grouping without extending fragile Layer 2 domains everywhere. Underlay health is critical because reliable Internet Protocol connectivity and stable routing are required for overlays to behave predictably, and control plane choices influence how mappings are learned and distributed. You avoid pitfalls like underlay instability that makes overlay troubleshooting confusing and maximum transmission unit mismatches that create fragmentation and performance degradation. You gain quick wins by monitoring both layers and remembering the anchor that the underlay carries packets while the overlay defines tenant segments. Assign yourself one underlay checklist rehearsal by describing what you would validate about routing stability, loss, latency, and maximum transmission unit before declaring an overlay problem solved, because that habit keeps virtual extensible local area network troubleshooting grounded and exam answers disciplined. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.